Have you ever been in my office? My office has fun things like this. Maybe your science teacher could teach you how to make one of these. You know, this thing, remember? Maybe you already know how to make one of these things. And then when you get to the end and you flip up the answer and it says, join a club. Do you see that?
Thank you for always bringing a positive energy. Thank you for always bringing a positive energy.
Gross. What was that?
Ahoy, matey!
Are you missing this? What number were you? Do you remember your number? Like first hour, second hour, third hour? Do you remember your number?
This is your scallywag, Arlo. Aye, aye. Here's the booty that we looted. Aye, aye.
Officer, whereabouts is the closest bank? It's right around the corner. Alright, cheers, thank you. Wait, wait.
What about this? What about this? Remember this? There's still May. May is still in your planner. You can still write things during remote learning. Now every day is not accurate.
Do you ever feel like a plastic bag drifting through the wind, wanting to start again?
Bears. Raiders. Bears. Raiders. Bears. Raiders. Bears. Guy Fieri.
Yep, it's official. We have totally lost it. All of us. We're gone.
So, what would you little maniacs like to do first?
Watching through our fingers, watching through our fingers. Shuts my eyes and count to 10. It goes in one ear out the other, one ear out the other. Burning bright right till the end. Now you'll be missing from the photographs, missing from the photographs.
This is the stupid stuff in chemistry that no one can ever do. Honestly, this is the hardest part of the year. I'm trying to teach it to you through a screen, so okay, here we go. So I think it's easier just to do it on a screen with you here. So I'm gonna go ahead and balance the equation. Yeah, that's a tough one. All right, how much hydrogen in liters of what? Okay, let's start with the BCA table. All right, so zinc, I got nitric acid. Yeah, subscript with zinc nitrate, and then I've got H2. All right, perfect. So anytime you want to make BCA, just throw it in there like I do. Put your reactants products before, change, and after. And here's the problem. We gotta go to moles for everything. So none of this stuff is in moles yet. So we'll go ahead and take a look at the zinc metal. All right, zinc metal, and then it gives me the nitrogen. Oh, there it is, 1.65 grams of zinc metal. So let's go ahead and take that zinc metal, and I'm gonna struggle here to figure out what color I want, and then a caps lock, yep. Oh, there you go. Okay, all right. So 1.65 grams, and go ahead and multiply that by 1 mole is 65.39 grams for the molar mass of zinc, just from my periodic table. Type that in my calculator really fast. 1.65 divided by 65.39. Let's just call that 0.25 moles ish. A little rounding there. All right, time to check the nitric. And here's the part that's new. The nitric is in a molarity. Awesome. It's like we're tying the whole year together right here. Alright, so molarity, if you didn't remember, that is equal to moles of solute per liters of solution. So moles per liter. What did the problem give me again? Okay, so the molarity is 0.5 and the volume's 80 milliliters, that is. Okay, so not to screw this whole thing up, so 0.5 molar is going to be equal to, I don't know the moles, but I know the liters would be 0.08 because it's 80 milliliters converted over with decimals. So I can use that information to solve for x, do a little cross multiply right there, double check, yeah, okay, 0.5, but yep, 80 milliliters. All right, so 0.5 times 0.08 gets us a whopping total of about 0.04 moles, we'll call it. Awesome. That's all review. Now we can do the stuff that's brand new. So we type it in. So 0.025 for the zinc. I'm gonna get rid of the moles here just because I don't want to type it over and over again. 0 and 0. Alright, change. So based off the balance equation, zinc goes down by 1, nitric goes down by 2, and then we'll just make 1 and 1 of each of the products. So when we're done, the zinc will be 0.025 minus x, which represents our change in the overall reaction. The nitric's going to be 0.04 minus 2x, and both products would just be whatever x is. Now, remember, we got to try and solve for what that x is. So I look at that ratio and I'm like, okay, I'm supposed to have double the nitric. If you can see it, you can already tell I don't have double the nitric. But let's play stupid. Let's suppose I have no idea. And I'll just say, okay, I have 0.025 minus x. Maybe that runs down to 0, and that's 0. So then x is 0.025. Well, let's double check that we actually have some nitric left over. So let's check the nitric. So 0.04 minus 2 times the 0.025. And that gives me an answer of negative 0.01. Oh, so I screwed up. Well, we didn't, but we just found out the nitric is actually the one that runs out. So the nitric is what we're going to use, the HNO3, to figure out what our actual X value is, not the zinc, because the zinc got us a negative number for our reactants to the nitric, meaning we ran out. So I plugged that in and ended up solving for X, and X would just be, 0.04 divided by 2, or 0.02. Now that 0.02 is technically in moles, and so that really means how many reactions took place. Okay, so what is this problem actually asking us? How much hydrogen in liters at STP can be produced? So we have the moles so far, but we don't actually know the liters just yet unless we think back a couple units from now. So the mole of hydrogen given by the BCA are 0.02. Okay, now a while back we learned that at STP, the molar volume of any gas is equal to 22.4 liters. That's super helpful. So, if we know we have 0.02 moles, and we know that 1 mole is 22.4 liters, we can basically just set up a conversion chart, or a ratio if you feel more comfortable solving it that way. Keep in mind you get to use your notes for all your testing for the remainder of the year, so you don't have to have this number memorized, and you can kind of just walk through to see this. So I multiply 0.02 by 22.4 liters, and I ended up figuring out that overall, as this reaction proceeds, I get about, 0.448 liters, or about 448 milliliters of hydrogen gas. And that's what I should theoretically get if I run the reaction to its completion, giving these starting values. Okay, so what is next? Well, question 2 asks us how much zinc nitrate can be produced. Now, it doesn't really specify what unit exactly, so we could just stop and say, hey, I know that the zinc nitrate is just going to be 0.02 moles because it's just an X. And I could just say, okay, the zinc nitrate is 0.02, but let's take this a little further. So I'm going to go ahead and plug in the X for everything on here. I know the zinc will run down, the nitric acid will run down to 0, zinc nitrate will be 0.02, and the hydrogen gas will be 0.02. And that's all, of course, in moles, so I can plug that all in there, and I'm not going to do for the first one just because I'm going to run out of space there as I sort of take a look at it. So the zinc nitrate is 0.02 moles. Well, let's assume the question asked for us to put it back into grams, because more often than not, that's what we'll have to do. That's not a difficult task for us to do. We merely just need to take what we actually started with, 0.02 moles, and convert it back using the molar mass. So I plug that in, and I'm going to go ahead and say, okay, zinc nitrate. So that's 1 zinc, and that would be, okay, 1 zinc nitrate. Oops, I have this flipped up here at the bottom. So actually it'd be 0.02 moles times the molar mass, in this case, zinc nitrate. And then we'd go ahead and take that and get roughly with 2 nitrogens, 6 oxygens, and 1 zinc, multiplied by 0.02, and I'll end up solving and figuring out that my zinc nitrate in this particular case is about 3.8 grams. And that's good enough for us, so we'll just go ahead and highlight that. Okay, what else is this question asking me? Question 3, which substance the zinc and nitric acid is left over? Well, that's obvious now because we've done a BCA table, and so we know that the leftover in this case is zinc. Next question, how much will be left over? So if we look back at our BCA, we know that the zinc will run down from 0.025 and go down by a factor of X in this case. So I'd just say my 0.025 moles, and I'd subtract out the 0.02 moles of reactions that took place, and I'd have 0.005 moles of the zinc left over, and we could stop. But again, we should probably put this back into grams. And so it didn't ask us to do this. This is just kind of going above and beyond, but more often than not it's going to say, hey, how many grams are left over? So we're going to want to take this back out of moles, because moles is not super useful in the everyday life. So the Mohr mass of zinc is 65.39. I'm going to multiply that by 0.005 moles. And if I plug that in real quick, I'm going to get a very, very small number, about 0.33 grams. But keep in mind, we only started with 1.65 grams of zinc, so we should end up with not a lot left. Okay, so we've got to be done with this problem, right? Highlight that answer. Question 5. What's the concentration of the zinc nitrate? Ugh, it just keeps going. Okay, so my zinc nitrate, the stuff at the top, we had solved in question 2. Well, molarity is moles per solute per liters of solution. Let me go ahead and type in an equation. Okay, got the fractions of moles per liters. Okay, so I'm trying to figure out this molarity of the zinc nitrate. Now, the nice thing about this is I already know the moles of the zinc nitrate because in my BCA table, I figured it out. So this, which is usually hard for us, is super easy. It's 0.02 moles for the zinc nitrate. The question then becomes, well, what's the volume of this solution? I mean, where's that coming from? And if you think back, we had 1.65 grams mixed with 80 milliliters of the acid. We're going to assume that 1.65 grams of zinc doesn't take up any space, because that's a pretty easy assumption. So the volume of our solution is not going to change. It's going to be 0.08 liters. And now this problem is actually really easy. It's just 0.02 moles divided by 0.08 liters. And if you really need a calculator for that, I'm sorry, but really that's 2/8 or 1/4 or 0.25 molar for our final concentration of our zinc nitrate. And if you notice as we go through this, that makes sense because we're producing some zinc and we're increasing its concentration overall. So go ahead and highlight. And then last, percent yield and percent error. Okay, so I haven't really talked about this with you guys just yet. It's one little addition to what we've been doing. So we know from question 1 that the hydrogen I should get is 448 milliliters. It says, well, what if we only get 300? So what's percent yield? For us, percent yield is your actual over your theoretical times 100. Wait, so what does that mean? Well, actual would be another word for experimental. So in this case, the 300 is like what you actually got from your experiments. The theoretical, in our case, would be what the math tells us. So we should get 448 milliliters. We only got 300. Your yield is basically like how much you're actually getting out compared to what you should. And we often express that in a percentage. So I'd type in my 300 milliliters as my actual. I would divide by my 448, which came from question 1, for our actual theoretical value. And then I would take that and multiply by 100. And you can already kind of see it's pretty close to 3/5. It's going to be a little bit less than that, I suppose. And in that case, or sorry, a little bit more than that, closer to 3/4. In any case, we find out it's roughly 67-ish% yield, which honestly is pretty good. If you had something like that in an actual lab, you'd be like, oh, awesome. But error then takes yield and says, okay, well, yield tells me about how much I should have got relative to what I really got. Error tells you how far off you are, and it doesn't care so much up or above. So when we look at it, you're just doing a subtraction from the actual and theoretical, and dividing by the theoretical again. So what that means is we're going to look at sort of how far it propagated from the accepted value. In our particular case here, we do the actual minus the theoretical, and those little bars represent absolute value. We really don't care if you go above or below, we're just going to talk about difference. And we'll compare to the theoretical and again multiply by 100. Now our actual in this case was 300. Our experimental was 448. So we're subtracting those two to see how far off we are from the correct value. And then we're going to compare that difference to the accepted value, or the 448 milliliters, because that accepted value will tell us how far we propagated from. And what's really weird about this, or interesting to me at least, is that your yield and your error will always either add up or subtract to be 100. And so you'll find your error in this case is 33%. And 33% error for us, we've done better. We've gotten below 5% in our class, but that's not bad for this particular case. So how do we actually sum up the hardest process of chemistry? Well, it's kind of just tying it all together. So when you take a look at a problem like this, realize that the only way to go through and solve this is first, we need to convert things to moles. So step one for us is converting to moles. Once we're in moles and we know the balanced chemical equation, we can work on the second step, which is using our BCA table to figure out how much gets reacted and how much is produced. And finally, when we're done, our final step of this process is putting it back into a workable unit, which for us is getting it out of moles. Either putting it into liters for a gas, putting it into a concentration for a solution, or putting it into a mass for a solid. And that's really all we end up doing. From here, it's just about practice.
Every minute and every hour, I miss you, I miss you, I miss you more. Every star